Let's start. I'm excited to have here today Annalisa Bruno. Thanks a lot for joining. Annalisa is an associate professor at Nanyang Technological University in Singapore and as visiting professor at Queen Mary University of London. She holds a Ph.D. in physics from the University Federico II in Naples and completed a post-doctoral research at Imperial College. I'm happy to introduce Annalisa's talk, which is titled From Precision to Scale, Thermal Evaporation Transforming Perovskite Device Design. And thanks a lot, Annalisa. Thanks for your time and thanks for joining us today.
Thank you, Daniele, and thank you, Darren, for this very nice invitation. It's my pleasure to be here today and to give an overview of our work of the last few years, where we have used thermal evaporation as a growth process method for metal halide perovskite to both scale up the technology, but also to explore different device concepts. So I will share my slides. And so we can start. Let me know if can you see nicely? Everything is good?
All is good. Thanks.
Okay, perfect. So today, as Daniele was mentioning, the title of my talk is From Precision to Scale. So thermal evaporation transforming perovskite device design. So if we want to maximize the use of optoelectronic devices, we need to look in terms of different solutions. So as we can see, if we move from solar farms to building integration to indoor lighting and utilities, we do need optoelectronic devices that are sustainable, but they also are very different. They may have different intrinsic properties. But at the same time, there are some commonalities among the different optoelectronic devices that we want, that we must respect all at the same time. In particular, if we look at maximize the use of both PV and LED, we need to look at devices that can be scalable, they can maintain high efficiency both on the small area devices and large area devices. They can ensure a good long-term stability, but maintaining low production cost with a low CO2 footprint, and they can be adaptable in different surfaces. With this idea in mind, really, perovskite in the last few years, metal halide perovskites have emerged as a revolutionary semiconductor materials for both this application, for PV, from photovoltaics, but also for LEDs, for transistors, photodetectors, and many others. But the real question that is common to all these optoelectronic devices is really how do we make the perovskite-based technologies attractive? Which are the main points that we need to that we require to the process? We need to develop a process that is customizable, so it can be easily adaptable to the different technologies, to the different optoelectronic device that we want. It should be fast. So guaranteeing in order to guarantee a good output, it can be reproducible and it must be scalable. So in a review that we have done a couple of years ago, we have looked at all the technology that have been successful in scaling up the perovskite from the typical lab size that is smaller than 1 centimeter scale towards large area devices. And as you can see here, all the red base arrow are at least one step based on solution process, while the blue ones, they have at least one process that is based on a vacuum process. All these technologies that we have seen here, they have been all successful in scale-up perovskite technology. Of course, the knowledge and the properties that we can have for all these different technologies might vary significantly. So, as I mentioned, this one, all these one on these sides, they all include some toxic solvent, while this one we can be classified as a more in general green process. Also, even if can further discuss about that. But what is really struck our attention that more than 99.5 at the time of writing this review of the paper that came out on perovskite, they were based on solution process material, while all the vacuum-based, it was just 0.5%. What does it mean? That the actual knowledge that we have on the vacuum-based process for perovskite is much less. So even if in the last few years, the vacuum process for perovskite are picking up, really the knowledge that we need to build up in terms of materials as device is still vast. But the really interesting question, besides the scalability of the device, when we look at the material level, which properties we can control with each of these techniques. And this is the kind of question that I will try to address beyond scalability and device performance. What happened at material level with the different techniques? What are the potential? In particular, my presentation today will focus on thermal evaporation, which is, again, one of the vacuum-based technologies, but has been widely used for example, for OLEDs materials. So it's a mature industrial technique that can guarantee a low roughness films with high purity that it comes intrinsically by the sublimation process. It can guarantee good uniformity of a large area, high thickness control, so we can go very large but also very thin. It can be intrinsically additive, so that means that we can build up multi-layer structure. It's surface conformal, can go in different, but it also is an intrinsic low temperature process, and it can also guarantee stability. And we will see how specifically. So here I will show you as a first part how we can customize the growth of the actual material, the active material, such as the perovskite, for different device architecture, and what we have done to customize it specifically, for example, for NIP and PIN devices. Then I will show how we moved from the small-scale device to large area devices, and how intrinsic properties, such as the control of the tensile stress within the perovskite, can guarantee an exceptional stability, both at room temperature and the high temperature. And also, we will show how this technique that can guarantee a very high control of the interlayers could also allow us to explore different device concepts for a variety of optoelectronic applications. So in my talk today, I will show how these four properties they can be achieved by using thermal evaporation in perovskite. So the very first thing that when we start our work on thermal evaporation, we started with the NIP devices. And we actually saw that with a combined approach based on stoichiometry control, interfacial optimization, and surface treatment, and optical treatment line management, we were able, by combining all this approach, to achieve efficiency that were above 20% for this solar cell. In a similar configuration, so when we move from the NIP to the PIN, the same active material was not able to deliver even comparable device. And all the same optimization that we had realized for the NIP device, it did not work for the PIN. So we look at how the perovskite grows, really the condition of growth of the perovskite material. What we have observed that basically the base pressure during the overall deposition time has been almost constant during the process. Here we were dealing with MAPI. So it means that basically the base pressure within the chamber is the pressure of the organic material. So in that case of the MAI. So in each point in time, we have a certain ratio between PBA2 and MAI. So we consider that if we were continuously varying the pressure within the chamber by controlling the amount of MAI that we have within our chamber, we were able to create a gradient of composition within our film. So to prove our concept, we grow films with different thickness, moving from 100 nanometers to 750 nanometers. And what we observed, the first thing is that we did some GWAX. We saw that 100 nanometer films, they are mostly oriented at 110 and 202, while when we move for 400 and 750 nanometer, we see that the PBI2 peak becomes an excess, while the 202 orientation remains dominant. To further prove that you have this gradient, we also studied it. We studied these films with angle-dependent X-ray, and we saw that basically when we move from the surface, from the GWAX 0.5 to all the way through 10 degrees, so we change this incident angle that you see here, the more increase this angle, the more profoundly we can observe the films. And we could see that the actual composition between the 10 degrees that integrates overall the thickness and the surface is completely different. So we further confirm that we create a gradient. And also UPS measurement further confirm that in this film, we do have a gradient of composition within our film. So with this, with the film that we grow in this way, we customize specifically for PIN devices to actually make it easier in terms of device structure, the charge flow within our devices. Also, in this case, we were able to achieve efficiency that were well above 20%. So just to give you an idea of how powerful is this methodology, and how this can be an alternative engineering way to engineering MAPI, methyl ammonium lead iodide. We see that basically the best performing devices with the PIN, they are obtained indeed with a gradient, and through a proper optimization, now we have achieved efficiency that are also exceeding 21%, while for the NAP devices, instead, since the energy levels of the HTL and the ETL is completely the opposite, the best condition is achieved where there is no gradient. And actually, our best performing devices are indeed obtained with without the gradient. So this is an example where we have the same active material, the same MAPI device, but a continuous engineering during the overall growth of the process can be customized for different device architecture. Just to put this in a context, even if compared to the state-of-the-art efficiency achieving 26%, it doesn't seem very high. Among the one step, the co-evaporation of metal halide perovskite, these values were above the highest when we reported, and also for co-evaporated perovskite, but also different groups have shown efficiency that now are around 21%. So when we were happy with the efficiency of our small area devices, we decided to move to larger area devices to actually scale up our devices. So what we can see here, that both for PIN and NAP, when we scale up our device, we move from 0.9, for example, from 10 centimeters square, we can see a drop in the efficiency, as you can see here. But if we look closer to the JB curve of both these devices, both for NAP and PIN, what we can actually observe that we have no losses in the current, in the JSC, and no losses in the VOC when we scale up. But actually, all the losses come from the fill factor, and this is due to an increasing of the sheet resistance of the TCO, which is actually a good news because it means that the high quality of the film is preserved. Otherwise, we could not have JSC and VOC that were maintained. And actually, just working on the geometry of the cell, so moving from a square-shaped solar cell to rectangular-shaped solar cells with a proper matching of the width and the length of our device, we were able to continuously scale up our solar cells without losing in the efficiency. As you can see here, same JC, same VOC, no losses in the JC. So with this design in mind, and understood the importance of this, we were able to design our own modules with the proper length and width, and we optimized with an efficiency that reached 18.7%, and with this was obtained with a very preliminary design of the module, when it was a manual scratching. Then when we moved to the fully laser scratch, we could maintain the efficiency. We improved the geometrical fill factor. For anyone that is not familiar with geometrical fill factor, the geometrical fill factor basically tells us how much of the module surface we cover. So ideally, we want it to be as close as possible to 100%, because it means that we are using all the active layer of our device. Since we are always looking at different way to integrate PV, especially in urban space, we are also looking at semi-transparent perovskite solar cells, and actually just working on the opaque top electrode. So we have not changed anything about our structures, but just changing the gold electrode with ITO of different thicknesses, we were able to obtain semi-transparent solar cells with different colors, as you can see here, both at the level of small area devices and modules. But the beauty of this approach is that basically we were able of not losing in terms of efficiency. So we have to have a constant efficiency around 16%, because it's which was due to the just to a minimization of the reflection, but no losses within the devices. So these values were reported, and the beauty of this approach of overall that I have shown to you is that even if this efficiency, you can see this is the co-evaporated efficiency, are lower than what we have with spin coating approach. When we scale up the devices to up to over 20 centimeters square, we have losses, picture losses that are less than 2%. When we scale up the size of our devices over 240 times. So up to now, I have shown you why by thermal evaporation, by thermal evaporation, we were able to customize our devices, and also the excellent scalability properties of devices prepared by thermal evaporation. Another property that I would like to discuss with you is the stability that you can guarantee by thermal evaporation. And this indeed depends to an intrinsic properties of the material. Why? So this is well known by spin coating, that when we spin coat our perovskite over our ultra-transporting layer or electro-transporting layer, and we want to fully form the perovskite, we do need to anneal. So during this annealing process, due to the difference of the expansion coefficient of the perovskite and the below layer, we can have a mismatch. So this mismatch of expansion coefficient between these two layers can generate a tensile stress or a compressive stress, depending, of course, if the expansion coefficient is larger than the below layer or is smaller than the below layer. And of course, this has already been shown that the either tensile stress is very detrimental for the stability of the perovskite, while the compressive stress or the absence of stress, it can be good for maintaining the stability. When it comes to thermal evaporation, when we actually evaporate our MAPI devices, what we actually have, that this is an image of the films when they come out from our thermal evaporator. As you can see, with the anneal film or the S deposit, they look exactly the same. The absorption is exactly the same before and after annealing, also the PL and also the SCM. What does it mean? It means that the perovskite is fully formed during the deposition process that happened at a low temperature. So when we have, even if we apply the annealing, which is actually not needed in this kind of perovskite, since there is not a formation of the crystal structure during the annealing process, we do not induce stress. So the way we grow MAPI by thermal evaporation is intrinsically tensile stress-free. Again, to further prove, we measure the XRD, where we see that there is no shift in the XRD before and after annealing, and also the device of the performance to further confirm that they showed no change in the device efficiency before and after annealing. This is very much different what happened with a typical XRD. So this is a XRD, a zoom of the XRD of the annealed thermal evaporated MAPI and the spin-coated thermal evaporated MAPI, where we can actually see very clearly that there is this shift in XRD. And again, the shift in XRD is always a clear signature of the presence of stress within our perovskite. So again, this is an intrinsic film stability. So we have studied the film itself with spire on top, and we have seen that basically even the bare film, without putting in a device, can maintain a very high stability when annealed for, this is annealing constantly at 85 degrees. We can see that the MAPI by spin coated is almost completely gone after 750 hours, but this is not the case for the anneal. And very nicely, you can also observe here that this is what happened for the when we anneal our solar cells. This is a thermal evaporated solar cells. You can see the cross-section SEM and the actual image of the cells. So you can see that you can see that the cells by spin coating is completely degraded after 3,006 hours of aging, while the one by thermal evaporation is completely intact, and also the interface is intact. So when we measure the performance under constant aging, we actually observe that we could maintain more than 80% for 5 months of continuous aging. So we are talking about 5,000 hours. And when stored in room temperature, this is completely unencapsulated devices in both conditions. We can maintain the same efficiency for 1.5 years. And again, this is due by the absence of tensile stress in our perovskite. So all that I have shown to you now is all based on MAPI, on pure MAPI, which has a fixed band gap. But we also have been looking on different approaches, again, to maintain the properties like the absence of tensile stress that is very desirable for our perovskite film, but also tuning the band gap. So the methodology, the hybrid methodology that we have developed is slightly different from what is usually done in the literature, where usually is co-evaporated or evaporated just the organic part before, and then is treated with the organic compound. In our case, we fully co-evaporated our MAPI, so we have a fully formed MAPI, and then we have a treatment with a very small amount. For example, in this case, it was MABR, and we let it stay for a certain amount of time, and then we spin coat it just to remove the excess of solvent. What we can observe that if we change this residential time here, we were able to basically to change the absorption, to change the absorption here, to shift the band gap from 160 to 170, and also the peak of DPL, we are able to shift from accordingly. And I'm sorry, there is this white part, but also we can see from the XRD that from 0 minute, you can see for 500 minutes, we can see a constant integration of the BR in the circle. This allows us also to achieve efficiency above 21% with higher band gap and very good stability. We also look at different optoelectronic devices. So we have started working together with Professor Soshi in August in NTU on light emitting transistor based on perovskite. And we did our first work in 2015, but it was based on spin-coated perovskite. But we also explored, then in 2018, we were actually able to show that the electroluminescence at the beginning was just visible at very low temperature. We were able to expand the range of emission up to 200 degrees. But still, to 200 Kelvin is still low temperature. So keeping in mind that the thermal evaporated perovskite show an absence of tensile stress, we decide to work exactly in the same configuration that we have used with the spin coated, but we just move to as active layer to thermal evaporated perovskite. So it's still MAPI in both cases, but here we use thermal evaporated perovskite. And as you can see here, we were able to observe light even above room temperature. And as you can see here, in the room temperature, this is actually the electroluminescence that you can observe in the transistor at room temperature. Why? What is happening? Again, the absence of tensile stress is able to minimize the ionic motion. And minimize the ionic motion, there is less recombination at room temperature, and so it's possible to create electroluminescence. We have seen some of the great potential of thermal evaporation. But if we move forward, as I mentioned at the beginning of my presentation, what we should do to make to a process that is really suitable to go further in the industrialization of the perovskite. We need to have a fast process. So how we can speed up this process? So in this review that came out at the beginning of the year, it's a perspective done by many groups that work in thermal evaporation perovskite. We have looked at the potential of the vacuum-based techniques. And as you can see, one of the main limitations is, besides the power conversion efficiency, is that all these different processes, they have a slow deposition rate. While to make this technique really suitable, we need to scale up in terms of course, efficiency, but the deposition rate, it must be faster of order of magnitude. And in particular, if you look at co-evaporation, we are all in this area. Okay, so the question that we ask ourselves, how we can increase the production rate without compromise the efficiency. So we have been looking at controlling the main deposition parameters, both at material level, so it means controlling the precursor temperature, the chamber pressure, but also the setup design, so such as source substrate distance and also the overall design of the chamber. So looking at material level, for now, we have been able to speed up our process of 6 times. Now, what is nice is that we are looking at the optoelectronic properties of this process, and what we can observe that from the slowest to the fastest process, where we go, so when we increase the deposition rate of 6 times, we were able to maintain the same optoelectronic properties. So we control the pressure, we control the temperature of our substrate, of our sources, and in order to maintain the same band gap and also a similar orientation, where 202 is always the main orientation, and as compared to the 102. And also in terms of morphology, as you can see, we have the same morphologies typical of the thermal evaporated perovskite with very small fluid. So in this condition, we were able to scale up our process to move from the typical 150 minutes to less than 25 minutes without compromising our device performance. And at the same time, since the annealing was not required, we also showed that also in this condition, the annealing was not required, making the process even overall faster. So just to put this in a context, these are all the work based on just on co-evaporated perovskite, where there are films that are in the thickness between 500 and 700 nanometers, and the deposition time, it can vary from 250 to 120 minutes. And while this is our recent result, where we obtain comparable efficiency with just 25 minutes. As you can see, this efficiency is slightly lower than also our own published result. This is because we did not apply any passivation, we did not apply any anti-reflection coating, because the idea was really to speed up everything. So just to make it, again, to put in a context, this is our result now. How do they compare with the other? But of course, to reach the target, we still have work to do. And again, there is still work that can be done at material level, but very importantly, we should move to the setup design of our system to speed it up. So as I mentioned at the beginning, thermal evaporation is is very successful in scale up the device over large area, but also it can give some other very interesting properties because we can control very precisely the thickness. So perovskite quantum confinement has always been an object of interesting research. Indeed, in the perovskite community, there have been many examples of quantization at material level. We have many examples of 2D perovskite, 1D perovskite, 0D perovskite, but this is all done at material level. Our approach is slightly different because we are talking about a structural level quantization. What does it mean? It means that our perovskite is still 3D, but we make it so thick with such a control of the thickness that is achievable just by thermal evaporation that the perovskite, even if it has 3D perovskite, as you can see here, we have 3D perovskite, and then we have an organic material that can also be inorganic as barrier. And we are able to create a multi-quantum well structure that it can become a superlattice. So multi-quantum wells, the concept of multi-quantum wells is again a multi-layer structure where the thickness of each of the films is comparable to the bore radius, so they are intrinsically quantized structure. And they've been widely used in 3.5 material. So at the moment, all the record efficiency for the 3.5 solar cells and LED are all based on multi-quantum well. So the concept of multi-quantum well is well established, but how we can realize this in perovskite? And also, which type of multi-quantum wells do we want? So according to the band gap of our perovskite and of the two semiconductor material that we put together, we can create a type 1 and type 2 multi-quantum well. If one of the material is completely embedded in the band gap of the other, or if they are staggered like this. Specifically, the type 1 multi-quantum well are very efficient for light emitting device, while type 2, they are better for light detection because they can maximize the transport property. So within the perovskite community, there have been few examples of multi-quantum wells, as you can see here, where they have shown that it's possible to tune the emission as we expected, and also to enhance the overall emission. But all this work that has been done up to now, they've all based on cesium lead bromide. So when we have a bromide, the ionic radius of the bromide is smaller than the one of the iodine-based perovskite. So what does it mean? That the possibility of shift and tuning the PL in iodine-based perovskite, it must be in principle much larger with iodine than bromide. So just to schematize how much we can shift by tuning the thickness of the film. So we look at multi-quantum wells with this idea in mind that are based on MAPIR to have a wide range of possible change, a wide range, and also to explore more the infrared region. So we look at two materials, in particular PCP and PBBC, that they have a good band alignment. And of course, they need to prepare by thermal evaporation. So with this, we created both type 1 and type 2 multi-quantum wells, as you can see here, and this is a typical cross-section. So the very first question that we asked ourselves, it was, is this material suitable for multi-quantum wells? What are the requirements to be suitable? So the requirement to be suitable is that there should be a minimal charge transfer at the interface. Why? Because when this film becomes very thin, basically, if we have a large change of the band gap, it can create a large band bending through the layers. And this is particularly detrimental for multi-quantum wells because they are very thin films. So in collaboration with our collaborator in Berkeley, we modeled what happened when we put the BPC and PPC on top of the MAPI, and we see that basically the surface are localized carriers and there's a limited band bending. So we can assume that there is a minimal band alignment disruption within our multi-quantum world. At the same time, we grow our films on different substrates to make sure that we could still have a perovskite, that we have a good band alignment, and the films are quite smooth. And as we can see, all these requirements have been achieved. So having a minimal band alignment, a consistent film morphology structure, we were able to start growing our multi-quantum wells. So we grow both type 1 and type 2 multi-quantum wells. And the first thing that we observe is basically that there was a shift as we expected. So these are single multi-quantum wells with different thickness of the organic layer. So the more we thin down our MAPI, the more we see that we reach the quantization stage, and basically we have a shift in the band gap, exactly as reported here, as expected. And the same things after for type 2. But what is a huge difference between these two quantum wells is that, so if you see here the MAPI, if we thin down the MAPI, there is a slight increase on the PN because of the intrinsic quantization of the MAPI. But if we put this MAPI layer within a single quantum well, what we can observe that in type 2, there is basically all the PL is almost quenched. While for type 1 multi-quantum well, we have an increase that is almost 50 times of the PL. And this is exactly as we expect it to be, because as I mentioned, the type 1, since the recombination it happened whole here, we have an enhancement of the PL. While in type 2 multi-quantum well, the charges tend to be easily separated at interface. So we also look at the ultrafast dynamics of type 1 multi-quantum wells. So we grow single quantum wells, as you can see here, with different thickness of the active layers. And we study the transit absorption. And what we can observe a shift of the photo bleaching peak, further confirming the quantization, but also very importantly, we can see also the shift in the peak, but also there is an increased recombination rate in a type 1 multi-quantum well. So lifetime of the photo bleaching state becomes shorter, as we were expecting. And also we were observing another thing. So if this is the peak energy for as function of the time for the different thickness of the film, what we see that it's for the 100 nanometer film, there is basically no change with the time. But the more we go towards thinner film, the more there is a blue shift in with the time, a shorter time of the peak. So this it could be consistent. It gave us an indication that it could be an increasing on the hot carrier lifetime. So in order to further prove this concept, what we did, we modeled our photo bleaching peaks with the normalization model. And what we actually, to extract the temperature, what we actually found, we found that with thinner film, the initial temperature, it is higher, but also the overall thermalization temperature is lower with the time. So we are able to slow down the hot carrier cooling. We also integrated our type 1 and type 2 multi-quantum well in different photodetectors. So for type 2 devices, as we were expecting, the photodetectors, they did not behave very well. There's a slight increasement as compared to the MAPI, but nothing major. But instead, when we realize our devices with our type 2 multi-quantum wells, what we can actually observe that there is a significant increase of the photocurrent and of course of the responsivity, both in the visible, but also in the infrared, so above the typical absorption of the perovskite because of the BPCP and the overall structure, because as we can see, the multi-quantum well response is even higher than the PBBC itself. So we have realized multi-photodetectors that they have high photocurrent and high response at low intensity, but also with a wider detection. So I've reached the end of my presentation today. I hope that I've shown you the versatility of the vacuum-based process in order to have a good composition control, excellent scalability, how the tensile stress can control the stability of the devices and the potential for multi-quantum wells. And I would like to acknowledge all the group, the people that you see red, they have worked on the multi-quantum wells, the one in yellow, they work on the PV devices, all the funding agency, Fluxim for the very nice invitation, and of course, all the group. And this is my contact.
This was an amazing talk, Annalisa, full of great results and information. Let me start with a general question. I know that you are an expert on upscaling of perovskite solar cells, and I would like to ask your take. Which are the challenges that we are still facing, both for evaporated solar cells and spin-coated, so solution-based solar cells?
Yeah, thank you, Daniele. Yes, there are challenges, of course. I mean, the field is proceeding very, very fast. As I mentioned today, for sure in the vacuum-based process, one of the main limitation is the time, because the process is not fast enough to keep up with the high output that is requested. Then stability, of course, is still, this is for both methodologies. I would say the stability is still a challenge to be tackled. And of course, for the solution process, there is still a problem with solvent. So there is an active research in looking in less toxic solvent, and it can be easier to be scaled up.
There is also a question that is similar to the one that I will make. To reduce the series resistance, you have been using a plain ITO, but there are also several technologies like using fingers or honeycomb made of, for example, very thin gold.
Yes.
Did you try any of these technologies?
Yes, we also tried that, and actually, when also in some other trials that I'm not showing here today, when we scale up, we also have tried with the thin fingers of. That again is an additional process. So if we can, the more we can minimize with the design, it will be eliminating one of the process to add.
Yes. There is a question here. I would like to ask you if MAPI is still a valid model for perovskite devices, knowing everything that we know today, all the troubles that this material has.
Okay, this is a very good question. Of course, MAPI has troubles, and but as also one of the major troubles, it comes from the stability, and the stability. This is where a lot of our work has been focused on, has been showing that by controlling the tensile stress, is it possible to have MAPI films that they can be extremely stable. So I'm not saying that it's the only material, but it's a material that can present still interesting properties much more than that was initially thought.
The semiconductor industry does photoresist spin coating over 300 millimeter diameter. Can we do this for perovskite instead of vacuum deposition?
Controlling the morphology will be more challenging than other materials, but there is not an intrinsic limitation as long as again it's a combination of the materials, the overall setup and the compositions and the composition and the morphology with a fine control of the morphology. This can be done.
There are a few other questions. I was wondering if you kept the organic salt ratio the same for all the position rates.
I think he's referring to the speed up process.
Yes.
Yes. Okay. So when we speed it up, actually, as you see from the XRD, basically we control the process, we optimize the process to make sure that we have the same composition at the end. Because if we just increase the rate, probably we ended up with a very different different composition with different film properties.
I've also questioned myself. We have been working on organic light-emitting transistors for many years, so with organic materials. And at the end of the day, these devices were working at very high voltage. Yeah, I'm not sure how to say it properly, but they were not good devices, right?
Yes.
Why did you start working on perovskite light-emitting transistors? What's your take there? What's your interest in these devices?
Yeah, okay. So we've started working on that for a couple of years. So in principle, I think this is what also I've been driving in the organic, is the idea that you have one device to do it all, right? Because a LED should always be driven by another device. So in principle, the idea to have one device is that it can drive the light emission and to have a very fine control of the space, because basically by control the voltage, you can move your emission line within the gap of the between the two electrodes. So in principle, you can have a very high precision with the voltage on the emission point. So there are these ideal advantages of these devices. And also in terms of material properties, it can give some interesting information about the material process. The overall applications on this, I still also I see challenges there.
There is another question here. Selina, you mentioned that annealing is not needed for your MAPI samples. So do you know this is a general true also for other composition when evaporation is used? For example, FA-based, and do you have any experience there?
Okay, no, I cannot say that there is a general state, but I will not exclude that with a further control. So at the moment, is for other composition is needed, and but I will say that with a further control of the optimization of the process, we could reach a good crystallization of the surface. On the surface that will not require other annealing after. But at the moment, no, it's still needed.
Okay, seems that there are no other questions, so I thank you a lot again, Annalisa.
Okay.
This was one single talk. Generally, we have two, but this time. Next time there is going to be another guest, is Diego Bagnis from Brazil, and he's going to present some exciting results on the fabrication of organic solar cells and perovskite solar cells again. Myself, I'm going to thanks again you and everyone that was here.
Thank you.
Merry Christmas, and I wish you all the best for the new year, and I see you the next year.
Okay, thank you. Thank you very much.
Bye.
Thank you. Thank you again. Bye-bye. Merry Christmas to you as well, and to everyone.